Okay, so should I be joining in the YouTube, or the participants will be joining using the Zoom link? Hello, I think Anantraj.
The- Yes, the students are also, they have the Zoom link also, and some of them are joined on YouTube.
So, okay, so they will be able to join the live interaction in Zoom link, but YouTube they can only view the interaction. Is that right?
Sir, yes, sir.
Okay, okay. So good evening, everyone. So if you have any questions, you can send the questions in the by the Zoom link. I will also just try to answer some of the questions which have been already posted using the Google form. Okay, so there was one question related to a simulation exercise. So, okay, so it was asked by, okay, Preet, regarding if the solution can be, okay, so the exercise can be submitted now and then will it be considered and reviewed? Yes. So if you are able to finish the simulation exercise, you can submit it through the forum, and myself and our TAs will be able to take a look at that. If you are having any issue in the simulation, that also you can post it. So we will try to uh, see if we can help out with your simulation. And there is another question by Rakesh. The question is, can you explain the difference between resistive load and a tuned load, inductor capacitor, working principle, voltage swings in an amplifier, active mixers, and reference reading? Okay. So starting, so with the reference reading, I think for the standard blocks which we are discussing in the class, those reference material is the same as what we discussed, which is already present in the website also. Okay, so you can follow the RF microelectronics textbook by Professor Razavi. You can also check the textbook uh, on the RF CMOS IC design by Professor Thomas Lee. In addition to that, if you want to know a little bit about the distributed circuits and distributed elements, then we have given the reference of Microwave Engineering by Ozar. So these are standard reference. You will be able to get the details about the standard blocks there. In addition to that, we are covering some new architecture, the recent trends in the RFIC designs. So those blocks like NPAth filter, and then you will be seeing maybe in the coming lectures about how we can do this digital, how we can use digital techniques like digital PA, how we can use RF DACs. So these kind of recent techniques, we are making use of the recent literature, and those literatures have been already put as a reference in the lecture notes. So I will encourage all of you to also go to the end of the lecture notes and see if there are some references mentioned there. Now, coming back to the question regarding the resistive load and the tuned load, that can be very briefly explained. So I will do one thing. I will share my screen here. Just a minute. I hope my screen is visible to all of you. Okay, so the question is regarding a resistive load and a tuned load. So this basic circuit, I think all of you already understand, where we have, let's say, a resistive load at the drain, and this MOSFET in common source configuration is used as an amplifier. So in this case, what happens? The VOA is equal to minus GM times the output load, which is RD into VM. So this resistive load in reality is not just the resistance. You also will find that there will be some parasitic capacitance at the drain node. And in addition to that, if you are also driving another stage, so that load will also come. So together, we can say that there is a extra capacitance at the output. Let's call it CL. So in such a scenario, your gain will modify to this new expression where we have this RD parallel coming with this 1 by SCL. So I hope all of you understand this part. If I have to draw the frequency response for this gain, so it will be easier if I just simplify. So I can write it as minus GM RD divided by 1 plus CL into RD. Okay. So VO by VN is the this expression. Is there any query? Okay, so this all of you understand, I hope. So the magnitude for this will show a simple low pass kind of behavior. So the magnitude response will look like this if you are doing in the log scale. Okay. So just F, we can do omega. Here we can also do in dV. Now this is a low pass behavior, and you'll find that this pole which is appearing at 1 by CLRD will be of the order of megahertz. Okay. Best case, you will be able to do maybe close to 100 megahertz. But when we are using this amplifier for high frequency application, we are operating somewhere here. Let's say this is your center frequency at which you want to the center frequency of the signal which you want to amplify. So obviously you can see that having a simple resistive load will not work for a high frequency application. So what you can do is you can see that there is this capacitor which is actually shorting some of the signal current at high frequency. So the current which is flowing in the CL, you can compensate by providing an opposite current through a inductor. So what happens is this inductor, if you choose appropriately, then the current in the inductor will be equal and opposite to the current in the capacitor. So such a circuit, you will find that at this resonant frequency of this L and C parallel combination, you will be having only the output impedance is RD, whereas as you move away from this resonant frequency, your output impedance is going to fall off. So it will appear as if this low pass kind of impedance which you are seeing just for the resistive load has been shifted to a higher frequency. So it will look like the same kind of impedance is now centered around the omega RF instead of DC. Is this making sense? So this low pass behavior, which is normally present, can be countered by providing current to the CL with the help of an inductor. So that is also called as tuned load because at a specific frequency where the inductor is completely compensating the current of this capacitor, we can get high gain. So this is CL. What you can do is you can add an inductor L such that this IC and this IL is equal and omega is equal to 1 by root over LC. So this you can ensure, and under such a situation, you'll find that if you look at your output, then your VO by Vin is going to be equal to GMRD at omega is equal to, let's call it omega naught. Okay. And you can actually write the complete transfer function. Okay. So if you write the complete transfer function, you will be getting a band pass kind of response. So you will be having a second order denominator along with a a 0 at origin. So the frequency response you are going to get will be looking like this. Okay. And here it is your omega RF to omega naught. This is called as tuned load. Now you can see that this grounding this inductor will be having some biasing issue. So that also can be resolved. We have seen one way to do is instead of connecting this to physical ground, we can connect it to the supply so that it is still incremental ground while connected across the CL. So you will be having circuit like this. Once you are using inductor for the DC biasing, so that the DC current can flow through this inductor. As such, you don't need RD, but still there will be some output impedance of this of this transistor. Okay, so and there can be some loss in this inductor. So all those things you can always club together in some effective RP. And now you can apply input here, take the output. This is called as tuned load. Okay, so the idea I hope is clear to all of you that earlier we were having the GMRD kind of gain at DC. Now we are having the GMRD gain at some omega naught. Okay, so this is the benefit of using this tuned load for high frequency application. So okay, so I hope the working principle of this tuned load is clear. The next part was related to the voltage swings in an amplifier and active mixer. Okay, so voltage swings as such we didn't cover in detail in this course. If you have taken some analog IC course earlier, there you might have already studied about this swing limits. Briefly here we can see that you want to always make sure the transistor which is being used for amplification should be in the saturation region. So for it to be always in the saturation region, and you can ensure that this gate voltage is such that it is or this drain voltage is at least Vg minus Vt, more than Vg minus Vt. Okay, so this can go only 1 Vt below this input. So based on that, you can find this limit on how much of the input voltage we can apply and what can be the swing at the drain side. For under some approximation, you can assume that if the gain is high, then the swing you can directly calculate based on the minimum voltage which is allowed at the drain side itself. Okay, so you know the gate voltage, the DC bias, the drain can go only some Vt, 1 Vt below the gate. So that is the minimum value. This is also called as Vd set. So that is the minimum value. The maximum value depends on the breakdown. Here, right now we are seeing that at DC, this VDD will be appearing as it is at the drain. Okay. So if you are going to have some swing, that swing is going to be on top of this VDD voltage. So you can choose a VDD such that even when there is a swing, the MOSFET is not undergoing breakdown. So that is a very important consideration. Many times to protect this transistor, you can also put a cascode element so that none of the transistors will be seeing voltage across the terminals exceeding the rated value. So this swing limit is basically you need to make sure the MOSFETs are operating in their intended region of operation. If there is some specific circuit for which you want to know the swing limits that we can discuss here, you can just let me know in the chat, or maybe you can just turn on the microphone and let me know. So it is assumed that at least you are already familiar with the basic common source amplifier swing calculation. Hmm. So if you know that, almost the same kind of technique you can use for swing calculation in the at high frequency as well. Yeah, so that a basic idea that the transistor should be operating in the intended region of operation, that will not change.
Yes, sir, I understood this.
Yes.
So my concern was that why it will not clip, the output will not clip above VDD.
Okay. Okay. So in this simple circuit, voltage will be going above VDD. Okay. So let's say we have applied an input and we are observing the output voltage. So there's a drain voltage, if you look, which is also the V naught in our case. Okay, so let me, this is VD. Your V naught is the AC component, the incremental component. So if we talk about the drain voltage, which has AC plus the DC, then we can see that the DC value, okay, so instead of talking about this, and we can also show that some V in has been applied like this. So what happens is this VD is at VDD to start with. As the input increases, your VD voltage is going to drop. And then again, it is going to follow like this. So the lowest value which you can allow this VD to go is VD sat. Which is going to be your VGS minus VT, almost VGS minus VT. Now the highest value which you can already see that in this circuit is going above VDD. Okay. Now, if VD set is let's say very small, 100 200 millivolts, then you can see that this peak value is going close to twice of the VDD. So when you're going to close to twice of the VDD, there can be some reliability issue with this transistor. So one way to prevent this is you start with a case where the VDD is already chosen to be half of the maximum voltage which this drain can go. In such a scenario, even when this voltage goes twice of VDD, the transistor is not going to undergo a breakdown. Another way is you can use a cascode element. So if you are using a cascode element, you can choose this V bias such that even when the output voltage, total output voltage is going close to VDD, this gate and drain voltage is still not exceeding VDD. Okay. And even the substrate of this cascode element can be connected to a voltage which is not exactly ground, but this can be chosen to be different from the ground. But what we will see is that when this voltage is rising, then this gate and the drain voltage is going to decide whether the transistor is going to break down or not. Okay, so that is going to be the most critical the critical voltage difference which we have to be careful. So as long as we can make sure this gate and drain voltage is not exceeding the VDD, you will find that the transistor is going to still operate, and you can, in such a scenario, maintain a high voltage at the output node while making sure none of these transistors are actually exceeding their breakdown limit. Now, many times whenever we are going beyond this VDD, it is also important to run some reliability simulation. So those simulation or those information you can also get from the foundry. So you can talk to them and then they will tell you about this part also. So how frequently you are exceeding the supply voltage or the rated value, and what is the duty cycle. So both of them factored together, they can give you a estimate of what is going to be the overall lifetime of such an amplifier. So these kind of optimizations you can do when you have access to this reliability model of the transistor. But one thing is important, that make sure the DC voltages never exceed the rated value. Whereas when there is a swing like this, okay, which is not always exceeding the, means which is not like 100% increase in the voltage between the terminals. In such a scenario, it is possible to exceed the rated voltage for some amount of time, okay, with some lower duty cycle. But yeah, the penalty is going to be in terms of the overall lifetime. I hope this part is clear. There is another way where you can again get a higher voltage swing at the output. That is by using a differential topology. So that also you can explore in case you have some issue in the output voltage swing. If you are talking about the LNA, in the case of the LNA, this swing is very low. Okay, input swing is also very low. Output swing is also very low. So under those small signal case, you can ignore this part. But when there are some large signals, we have to be really careful.
Yeah, got it. Thank you very much.
Okay. Now there is a comment here, is this conductor affects any pole in frequency response? Oh yeah, so you can see that if we have this tuned load, okay, this tuned load is going to add a complex pole. Okay, depends. Okay, depends on the damping. Okay, so it's a second order system. So you are going to have an equation where we can write it as going to be this current which is flowing in a parallel combination of L, C, and R. So you will be having so you are going to have I GP plus SCL plus 1 by SL. this kind of transfer function. And you can already see that it is going to have SLGP is nothing but 1 by RP plus 1. So this kind of transfer function you are going to get. So you can already see that earlier we had a pole which was at 1 by RC. Here now we are having a second order system. So this is going to have either two real poles or two complex poles. Okay. And that will be dependent on what is going to be the damping factor or the quality factor of this output load network. So of course, yeah, it is going to affect your pole location. But good thing is you are getting a zero at DC. Okay, so you are having a frequency response which starts rising from DC. But then if you have, let's say, under damped system where your quality factor is more than half, then you will be having complex poles. And both the poles are going to appear at magnitude of omega naught. So depending on the Q, you will be having some kind of peaking at this frequency, and again, you will be having roll off. Okay, so the two poles are going to add a minus 40 dB per decade roll off, and since here you had a 10, so you are increasing at 20 dB per decade. Okay, after those two poles, now you will be rolling off at minus 20 dB per decade. Okay. So in this frequency response, it is assumed that the poles are complex. So at omega naught, you will be getting the effect of both the poles. Is this clear?
Yes, sir, it is clear, sir. Sir, one more doubt I have, sir. Actually, I'm making one receiver chain, means not in that high frequency, in the kilowatts range, that is basically for ultrasonic and for sonar application. So actually, our sensor is variation is means, for example, an array is there, transducer array, that is means elements are not normalized, means different tolerance is there for the sensor. So for keeping the receiver chain, so first is, for example, a LNA, then a filter, then a second stage gain we are keeping, that is for normalization for all the elements. But the problem is, sir, whenever the filter, for example, you are keeping some 200 kilohertz center around and some 10 to 20 kilohertz bandwidth, but when you are keeping the second stage, that is having a flat band. So again, those out of band noise, again, it is become increasing. Means SNR point of view, so it is nothing, any improvement is coming. So how to means modify or any other ideas, sir?
So what you are saying is, let's say you have two channels, and two channels are there. The two channels are having different frequency response. Is that what you are saying?
No, sir. Frequency response are same, sir. Means all the transducer will get the same frequency band, but the
Okay.
electrical output of the elements will be different. So for that, we are keeping second stage to normalize, means normalize the signal
That
before
is
giving to
only the
ADC.
gain part, is it? So some one channel has a higher gain, another channel has lower gain.
Correct, sir. That is the sensor sensitivity is still like that, sir.
Okay, so you're trying to so making sure all the channels have same output voltage.
Yes, sir. Before going to ADC.
Okay, so that is a very common scenario. Okay, so although so far in the receiver, what we are seeing is are also as such single channel, single antenna system, but within that also you might have seen we have I and Q. So those I and Q channels also will be having some mismatch in the gain as well as phase. So what is done is we have to do calibration, and many times we just try to do this calibration in the analog domain itself. So for example, as you are saying, you have a variable gain in the two paths, correct? So you have to run a calibration loop to make sure that gain in both the paths are equal. And if that is not sufficient, but you have independent ADC for both the channels, then what you can do, you can match their gain in the digital domain as well. So you can look at this option if you are having independent yeah, digital samples, then you can match their gain more precisely there. But still, yeah, there should not be huge variation in the gain in the two channels. That you should try to calibrate in the analog domain.
Okay, okay, sir. But for sir, for second stage, that is having a coming very wide band, means gain is giving because filter is giving some 200 kilowatts centered about and bandwidth is 20 kilowatts. So that much signal is giving to the second stage for normalization the gain. But when I am tuning the normalization of the gain in second stage flat gain is coming throughout the band up to 100 megahertz. So the filter out of filter also again it is increasing.
So I understand this second channel. Huh? So you have second channel which has
No, sir,
a
not second channel. In the first
second,
channel itself, the
two stage.
stages are, for example, LNA, then a band
Yes,
pass filter, then
right.
a second stage VGA.
Okay, okay. So the VGA you are saying is not doing the filtering.
Yes,
VGA is
yes, exactly,
doing.
sir, exactly. So again, it is
Okay.
increasing, sir.
No, so what happens is if you have a VGA, which normally you will try to ensure that any signal or noise is dominated by the initial stages. Hmm. So the final stage, the VGA, even though it will add noise, let's say, but that noise is going to be much smaller compared to the noise coming from the initial stages. But let's say its noise is dominating and that noise is appearing because you have to do some sampling, correct? So you need to make sure before sampling you do this anti-aliased filter if the VGA noise is dominating. Normally, your gain should be good enough in the initial stages such that the noise of first initial stages will dominate in the output, not the VGA noise. That is how you should try to do the design. So, VGA noise, if it is coming, especially in the out of band, if the VGA noise is dominating, what you have to do is you have to put a filter. Otherwise, it will everything will come in band after sampling.
Okay, okay, sir. So, sir, then LNA gain should be more than the VGA gain.
LNA gain you should keep as high as possible while making sure even for the maximum input signal there is no clipping anywhere. Hmm. So LNA
Okay,
gain
okay.
you will try to keep as high as possible. Okay.
Mm-hmm.
Once that has been done, so in LNA it's also actually we add programmability. I don't know whether it is feasible in your scenario. So for
Yes, sir, it is there,
example,
sir.
it's there,
Programmable
correct?
option is there. 6
Okay,
dB stepwise option is there.
option is there, correct?
Mm-hmm.
So I think so you are talking about the case when the input signal is really weak, correct? So you will be using maximum gain of the LNA.
Yes, yes, yes. Correct, sir.
And in such a scenario, second stage, if it is adding a lot of out of band noise, yes, you should do filtering. That is important. Some of
Mm-hmm.
these ADCs have inbuilt filtering because of their structure, but it's better you add one more stage of filtering before feeding to the ADC.
Okay, okay. Thank you, sir. I'll see that one definitely.
Okay, so any more questions? Regarding this tool access, so this LT Spice is a very simple and user-friendly tool, very easy to install and use it. But what happens is, if you want to do a little bit more and detailed design where we also want to capture the layout effects, in such a scenario, it's better to use a different tool flow. So, for example, I have shared one link, okay, in the second and third simulation exercise, link for this ng-spice based IC design tool flow. So in that link, if you go, you will get a Docker image. Okay, that image you can just install, and it will have all the open source tools installed in one place along with the open source PDK. So the open source PDK have your standard MOSFETs and the other passive devices along with their layout, and you can use that this GUI based schematic editor, that X schema. So that X schema is there. You can do the schematic editing. You can do the simulation using ngSpice, which is already integrated in the tool flow. And after that, you can also do the layout editing in Magic. That is also present. Okay, it's all integrated. It's all put together using with the help of some scripts there. So if you want to understand some more and practical effects in this high frequency design, you can try that flow. And in addition to that, let's say if you have already access to either Mentor graphics or cadence based IC design flow, that is really useful, because in that flow you will be able to do some advanced RF analysis, which is very useful when we are talking about this mixer kind of simulation.
Sir, for low frequency application, can you please suggest any reference books, sir? Like up to megahertz level designing and those things.
Yeah, so if it is using off-the-shelf components and you want to do the design, that this Cedar Smith is a very good reference book. Okay, Microelectronics by Cedar Smith. Then, so that will give you a lot of fundamentals about designing analog circuits using transistor. And if you have a lot of op amps in your design, then you can use this reference book by S. Franco. Okay, so applications of operational amplifiers. I think that's the textbook name by S. Franco, Sergei Franco. So in addition to that, if you are doing custom IC design at low frequency, then there is a standard textbook by, again, Professor Razavi, Design of CMOS Amplifiers. Or I think so. The textbook name is not Amplifier, Design of CMOS Integrated Circuits. Okay, so that is anyway. So that is a well-known textbook. Then there are some other textbook which talks about different kind of topologies. For example, there is a textbook by Ken Martin. So where you will be finding a lot of circuit topologies, especially all these standard high precision analog systems. Then there is a classical textbook by Gray Mayer, which is mostly based on bipolar devices. But those bipolar devices techniques can also be used for the CMOS devices. So, so these are anyway textbook. In addition to that, in NPTEL itself, you will be finding very good video lectures, which talks about this analog circuits design, analog IC design.
Okay, thank you. The power amplifier side design, these books are sufficient, sir?
This is for high frequency or low frequency?
Or low frequency,
Okay.
high power.
So for low frequency power applications, so these books will give you a basic idea about signal understanding. They may also talk about this class A, class B, class AB kind of biasing. But the practical issues with respect to the high power these amplifiers will also require you to have some background in the some kind of power electronics, because those power electronics community very regularly handles very high voltage devices where you need to also be worried about the thermal part. Just for this thermal consideration and this, if you are doing, let's say, some transistor level design on a PCB, you need to be, and your voltage levels are exceeding, let's say, hundreds of volts. So I guess the application which you're talking about, the voltage levels may be exceeding easily 100 volts. Those transducers can be very difficult to drive. So such a scenario, as such, I am not aware. Okay, so again, yeah, so don't have a lot of experience in such high voltage, low frequency amplifiers, but you'll get some good reference from this power electronics community also. In addition to the standard, this microelectronics by Cetera Smith, for example, if you take a look, it will talk about how to understand the large signal behavior of the transistors. But you may have to understand this practical consideration related to the thermal as well as the breakdown. So not only breakdown of the device, the transistor, you need to be also careful about separating those signal traces far enough such that the PCB which you are using can also handle this high voltage. So many times you may have to add a lot of slots between the between the lines, so that, and you have to also use a lot of grounding. So these are a lot of practical issues which will come when you talk about high voltage amplifiers.
Hello, sir.
Yes.
Sir, I am actually designing one LNA at X-band frequency from 9 to 10 gigahertz bandwidth. So I am having a doubt like which PDK to be used, like 130 nanometer CMOS and 65, whether it is realizable at, suppose we want a 2 dB noise figure. So how we'll get to know which PDK is better for the design?
Okay, yeah. So if you want to just, let's say, test the technology, what you can do is you can, let's say you have access to this either Cadence or ADS or this mental graphics based simulation flow. So what you can do, you can find something called as NF-min. So you can take the transistor and you can try to find what is the minimum noise figure if you use this transistor by sweeping the biasing. So you don't have to design entire LNA. So you can find the NF-min and directly from the S parameters, and you can control its gate overdrive. And normally you will be using the minimum channel length to get the NF-min. So based on that, you will be able to say if your NF-min itself is coming above 2 dB, then definitely when you use your actual devices or actual biasing, it will add more noise. So if you are targeting somewhere around 2 dB, it's better to have an NF-min, which is, let's say, around 1 dB, 1.3 dB, something like that. So the technology cannot support an NF min much below the 2 dB, then there is no point in using the technology. Okay.
Yeah, okay, sir.
And for X band, 3130, you will be able, you should be able to get. You may have to see how much bandwidth you want to cover.
My sir, 1 gigahertz.
Instantaneous bandwidth, is it?
Yeah, and gain of around 20 dB, sir.
Okay. So 20 dB gain with a sub 2 dB noise figure. So around 10 gigahertz, 1 gigahertz bandwidth is what we're targeting, 10%.
Yeah, yes.
So this bandwidth also can be challenging. So you have to see if the instantaneous bandwidth. You may be able to get a bandwidth, then effectively you will be adding some loss to increase the bandwidth. Then your gain may come down. So there will be some trade-off with noise figure. But just if you want to look at the noise figure, you can try this NF-min simulation. You may be able to just hit 2 dB at 10 gigahertz, but you just try it out.
So we have to use a common source topology for NF min.
So for NF min, yeah, so NF min, you don't need to worry about this degeneration. Okay, just take the MOS in the common source. So effectively, it will try to see if all the matchings have been taken care using some lossless components. Or you are able to show an optimum impedance at the input. So you don't have to do based on the S parameter automatically, it can figure out what is the optimum impedance. So under that case, it will give you the NF min. Now, in practice, when you are going to do the design, you need to also do power matching. Okay, just noise matching is not enough. So you can use this inductive degeneration technique. Inductive degeneration will give you the minimum noise figure as well as it will also give you the impedance matching. NF min, you should just use the MOSFET in the common source. You don't have to worry about the power matching for NF min.
Okay, sir. Okay.
Okay, so if there are no more questions, we can end this session here. If still you have questions, you can always put your queries in the discussion forum. Okay, thank you, everyone.
Thank you, sir.